So now we're going to start talking about the fundamental things inside of an instruction set architecture and the things you need to build inside of an instruction set architecture. And we're going to start off by talking about machine models. So I have a question here. Where do operands come from? And where do results go to? So when I say operands, these are the data values that you're going to operate on with a single instruction on a processor. And the results are where they, the data that gets calculated. And where does it go? And this is actually an instruction set architecture or a big A architecture concern. Fundamentally, you're going to have some form of arithmetic logic unit or some sort of calculation unit. And you're going to have some type of memory storage. And in a processor, you're probably going to want to take stuff from the storage, move it to the ALU, compute on it, and then put it back into storage somehow. And this is the processor here that we wrap around the ALU. And the machine model is what is the implementation, what is the semantics, or excuse me, not the implementation, what is the organization of the registers, how do you go to access memory, what sort of instructions and operations are allowed. And we're going to talk a little bit about where do the operands come from and where do the results go, and different machine models that people have built. So this is different instruction set architectures, and even more than instruction set architectures, because instruction set architectures talk about how do you encode instructions even. This is even a little bit more fundamental of how do you go about reasoning about how to move data from memory to the ALU and back, and how do you go and store the data close to the ALU. So let's start off with a very simplistic example here, a very simplistic processor that people have actually built. Believe it or not, you don't have to have registers in your processor, or you don't have to have named registers in your instruction set architecture. Instead, you can have a stack. A stack is just a storage element where you put things onto the stack, and then they come off in the order that was the last one that was put on there that gets taken off first. Instead, in a very basic sense, we just take the top two things on the stack, we fetch both of them, operate on them, and put them on what would be the top of the stack. Building up from there, we can think about something like a accumulator architecture. So typically in an accumulator architecture, if you have one accumulator, so there's only one register, one of the operands for every operation you do is always implicit. It has to come from the accumulator. The other one, let's say, can come from memory. So you have to name one of the operands in an architecture like that. Building up from there, we can start thinking about maybe register to memory operations, where you'll name, let's say, the operand that is the source, let's say coming from memory, and you'll name, let's say, an operand coming from your register file. And optionally, you may even name the destination. So these are all options, and we'll call this a register memory architecture. Finally, we have something like a register architecture. So everyone wager guess here, how many named operands do we have here? 3. OK, yeah, and so this picture here, we're going to take something from a register, something from another register, and we have to name where to go put it. So I wanted to point out here, actually, the number of explicitly named operands for some of these is a little bit more questionable than others. So as you can see here, we have 0. We have a little more complicated something where we have 1, 2, or 3. Now, why do I say 2 or 3 here? So some of these architectures or architectural models don't necessarily name the resultant or the result location. Some of them will implicitly name the result. So something like x86, for instance, the first source operand is always the destination. So it only has to name two things. Something like MIPS, or most RISC architectures, will actually name all three. And you can think about that happening with both memory and a register-register architecture. So a good example of a 3-operand memory, which I don't have drawn here. I just have register memory drawn here, but memory, which basically says all of your operands come from memory and all your destinations are in memory, is something like the VAX architecture, which was popular in the 70s. You could actually have all of your operands come from memory, do some operation on them, and store it back into memory. So one interesting trade-off here is as you start to have more operands that are explicitly named, you need more encoding space for that. And this is one of the important trade-offs. Okay, so let's go into a little bit of depth about a stack-based architecture. So some examples of this are actually the Burroughs 5000, the Symbolics machines were stack-based, and these are sort of machines from the past. There's a few modern or more modern examples of this. For instance, the Java virtual machine is actually a stack architecture. And then also Intel's old floating point system, x87, they've since sort of deprecated this, but it's still relatively modern. It was a stack-based instruction set architecture. Let's take a stack-based instruction set architecture and look at how you can go about evaluating an expression. So here we have an expression, a plus b times c, all in parentheses, that whole quantity divided by a plus d times c minus e. So it's some complex math instruction or math operation that we need to do. Here we actually break down this into a parse tree of this. So you can see this is preserving orders of operations. Well, we have a plus this subquantity here of b times c. You take all of this and divide it by this sub-expression here. And a little bit of a throwback here. This is a way that we're going to take the operations, and if we do these operations on a stack machine model, we're going to get the right result. So what this means is put a on the stack, put b on the stack, put c on the stack, and then multiply b times c, and then add the result times a, and you can see that we're going to build this expression on a stack. So it's sort of a different way to sort of rethink about problems. And we'll walk through an example here. So here we have an evaluation stack, and the top of the stack is going to be whatever's on the top here in this picture. So first thing you're going to do is we're going to say push a. So a shows up on the stack. Then we're going to push b. We're going to push c. And then we're going to do a multiply. So we're going to take the two entries that are on the top of the stack, multiply them, and put them into this entry in the stack. And then we're going to say add, and it's going to add the two top things on the stack here and put the result here. And you can see that if you run something like this, you can actually do full computations on a very small stack. And what's also nice here is you don't have to explicitly name any of the operands. So this machine model allows you to run real programs. And one of the things I wanted to get across here is that the stack is part of the processor state. And it's usually, so that's the big A instruction, or big A architecture, or the instruction set architecture. You have a stack, and many times it's unbounded in the big A architecture, but in real life it needs to be bounded somehow, because you can't have infinitely long physical stacks in your machine. So it's conceptually unbounded, but you probably want to have it overflow to main memory if you put too many things on the stack. And this is an important characteristic, because otherwise there's certain computations you can't do. If, for instance, the parse tree is too long here, or the depth of the tree is too long, your stack might grow too long. OK, so let's say we have a microarchitecture implementation of a instruction set architecture, which is a stack-based architecture. And the top two elements of the stack are kept in registers. And the rest is in main memory. And it spills and fills. Well, each push has a memory reference. So when you put something on the stack, it has a memory reference. And each pop has a memory reference, because you need to put something back into main memory. But more so than that, you might have extra memory references here as the stack spills over into main memory, and you might have to pull something back in from main memory. So that's not very good, because you might end up with a push having more than one memory reference. So one optimization from a microarchitecture perspective is you can think about having n elements of your stack in registers very close to the processor, and only have to go access main memory when the register stack overflows and underflows. So instead of having to do a memory reference basically every single time you do an operation or every single time you do a push or a pop, you do it only when the stack depth gets too large that you can't fit everything on your stack. So let's walk through a brief example here. We have the same expression calculation that we were doing before. And you can see we can do push, 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 multiply, add, push, 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 multiply, add, push e, subtract, and then do all the divides at the end. But if we have a stack size of 2, what's going to happen here is at the beginning, we're only going to, when we do a push, we're going to do a load from A, push, we're going to do a load from B. Now we do a push of load of C, but our stack already has 2 things on it. So when we try to push the third thing, we have to overflow the bottom of the stack somewhere. So we're actually going to do a stack save of A out to main memory. Here we do this multiply, and we actually have to do a stack fetch of A and get it back from main memory. So it's a lot of extra memory operations. So you might want to think of a different microarchitecture. And if you sort of walk through this whole example here, we're going to see that we have 4 stores and 4 fetches for main memory, which are all implicit, plus the explicit ones that we're trying to do with the pushes and the pops. Well, that's 8 extra memory operations. Can we think about how to build a microarchitecture which has less, but has the exact same instruction set architecture? Well, let's say we have a machine which has a stack size of 4. Well, if the stack size of 4, at the worst case here, we only ever have to fit 4 things on our stack. So we never have to spill out to main memory, our stack. Pushes and pops still have to access memory, but that's what they're trying to do. They're actually trying to access memory. So to sum up here about stack-based machine models, they look pretty cool, but not all things are great at all times. So one of the interesting things here to see is we actually push A, and we push A again. So we're doing redundant work. And we push C, and we push C again. C and A had the same value both times we pushed them. So all of a sudden, we're doing extra work, and maybe we could have done less work if we had an architecture or a machine model, a big A architecture, which allows you to store multiple things and name different operands. So what I want to get across here is, while a stack-based architecture is very simple, the instructions are very dense, it may not be good for performance because you might end up having to reload values multiple times. Versus if you had an instruction set architecture, something like MIPS, where you actually have 32 general purpose registers, and you can name any register for any instruction, you could have loaded A, B, C, D, and E all into the register space once, and then done all your operations, and never have had to reload. And this is actually an instruction set issue, and not, or a fundamental machine model issue, and not a microarchitecture issue. OK, so to summarize different machine models, we have our stack, accumulator, register and memory, and register, sometimes called load store architecture. If we want to take some expression here like C equals A plus B, we can look at the instructions that would have to be generated on an abstract architecture. So here we're going to have push A, push B, add, pop C. As we add more naming, we actually can potentially have fewer registers, or fewer instructions, excuse me. So we load A, add B. Note here, we don't have to name what we're adding with because we're adding with the accumulator. And then store C. Start to get a little bit more compact. If we have register memory, we can load one of the values, add, store. It's pretty simple. If we have a load store architecture, we actually have to do a little bit more work. We have to load, add, store. But which seems inefficient, but if you have to reuse any of these values, A, B, you don't have to go reload them, versus in these two architectures, you have to go reload the value.